Sort of perfect. We'll see what happens when I have to do some demos. Bonjour Can, ça va? Très bien. That's all the French I'm going to speak because that's about all the French I can speak. So hi, yes, I'm Alex. I am Aching Brain on the internet. And my talk is on libp2p over HTTP. We actually have a competition to see who can say libp2p over HTTP over libp2p over HTTP the most to people this week, and at the end of the week they'll get a prize, and I think Dave might be winning for that just now. So
yes, I have prizes.
Check the leaderboards. It might be a whole bunch of libp2p t-shirts at this rate, I think. Yeah, the reason the talk's like that is just because it's these words just they lose meaning after a while. So that's the talk. Yeah. So hi. So I'm Alex. I'm Aching Brain. I work for Shipyard. We're a group of engineers. We were formed from the IPFS and libp2p teams and protocol labs. We look after popular IPFS implementations such as Helia, Kubo, Boxo, Rainbow, IPFS cluster, and in libp2p land, we look after JS libp2p and Go libp2p. And I am the maintainer of JS libp2p, and it's what I spend most of my time working on. Today, I'm here to talk about HTTP. And historically, HTTP has not been a very good fit for libp2p. It is client-server based rather than peer-to-peer, and it very much lends itself to centralization, obviously being client-server based. It's accessed via URLs, which means that you already have like a centralized like domain registries. It's based on DNS for the most part if you're using domain names, which is easy to spoof. It's easy to censor and deny access. You can serve any old content from a URL, so you're not guaranteed to be getting the thing that you requested, and you might never know. The security model for HTTP is generally TLS, SSL. The certificates that are required for this, they can only be created by a few blessed organizations. They don't verify identities. All they really verify is that you've paid some money to someone. Let's accept it, of course. The security model, it does prevent eavesdropping for the most part in some cases. So this is the idealized version. You just make a request to the server and it goes over TLS. That's fine. What often happens is this kind of thing, particularly in enterprise environments where if you have a root certificate installed on the device or a compromised root certificate, then intermediate servers can mint any certificates they like, and then they can inspect all the traffic as it goes through, and you would never know. But it's not all bad, HTTP. What would be nice if we could ignore some of the bad bits and we can just take the good bits. So like, what's good? I mean, there's a lot of existing infrastructure out there that we can use. Like, so you have edge networks and you have like caching and all this kind of stuff. But at the moment, libp2p kind of struggles to take advantage of this kind of thing. If you ignore things like cookies and stuff, then, or even including cookies, like HTTP on its own lends itself to stateless architectures, and we love stateless architectures because it means that it's very easy to scale things. If you can include all the data in the request that you need to process the request, then you can scale horizontally, and that's fantastic, and it generally leads to simpler application design and better scalability. It's widely supported. It runs everywhere. Yes, web browsers, but also every single computing device, pretty much from supercomputers down to wearables and Arduino-based microcontrollers. They all have some method of making an HTTP request. So this is quite useful. If you could be doing libp2p-ish things on all of these devices, that would be incredible. So what do we want? Stateless HTTP. We want simple request response protocols, stateless architectures, clearly defined semantic layer, and a dependency-free libp2p in clients via like web browsers, just via like window fetch or curl or whatever. So how do we get it? Right, well, if we kind of narrow our definition of HTTP to just what's in RFC 9110, which defines HTTP semantics, it defines it as and I will quote, a stateless application level protocol for distributed collaborative hypertext information systems. So we're not talking about transports or encoding or anything like that. We're going to decouple HTTP as an application protocol from the underlying transports and things. So really, we're just talking about headers and a body. Just nice, simple requests and responses. And then it would be nice if we could then also let libp2p do the networking layer, and then you can take advantage of things like NAT traversal, streaming, authentication, encryption, and all that kind of stuff. So what would a libp2p protocol running over HTTP look like? It might look a bit like this. This is the ping protocol ported to HTTP. So we send 32 bytes of data, and then we read 32 bytes from the response. Very simple. Great, there you go. Because we've defined a protocol, and we can call it libp2p. That's fab. One thing is, you might notice that we're making a request. This has been clipped off the screen, but you can't see it. But we're making a request to the root, which is really tedious because it means that you'd only be able to serve one protocol. So instead, if we could do some protocol discovery, that would be quite cool. So libp2p has an HTTP spec, and it defines this well-known URL. Well-known because we've called it well-known. Self-fulfilling. So this contains protocol to path mapping. So if I do a simple get to this URL, here I'm piping it to JQ, and I get this JSON document back, and it tells me a path where I can reach it. So we've got the protocol ID, and then the path that it's available on. And then it's an object so that we can include additional metadata in there later on if we need it. So then instead, I do a request to HTTP ping /1. I send some data and I read back. And now I have my protocol running under a path, which is great. So that is the basics of libp2p over HTTP. It's just a web browser that makes a request, or it's just a client that makes a request to a web server, which then hands it off to libp2p for processing. So let's have a little demo. Somehow. Oh my gosh. I'm going to try and make this more legible. Not only bigger. Oh God. Yeah, I'm going to make the screen white. I'm going to bring it back over here. And then I mean that's, oh God's sake. Talk amongst yourselves. There we go. Should have done that first, Alex. Okay, cool. So here I have a simple server. So I'm creating a node, and I have the services, HTTP services. Now I'm going to register a handler for the HTTP protocol. So I have a protocol path, hello world, and then it accepts a request object. So this is your bog standard MDN like request that you use with fetch, and then I return a response object. Just going to say hello. I have a helper method which I pass the libp2p node to called canHandle. Well, the function's called canHandle, and all it does is it checks with the HTTP service registered with the libp2p node. Do you have a route registered for this request? I'm going to create a simple web server. So this is just the built-in node web server. I call did handle with the request and the response. If it returns true, it means libp2p handled the request. If it returns false, then it means it didn't, and so I need to fall through to something else. So I'm just going to return a 404, and then I will listen on a port. Hooray. That's it. That's all. So if I start my server, it's listening. So I can do... So the first thing I want to do is I want to find out where my protocols are hosted. So I've done a curl to well-known libp2p protocols. I've looked up. This is the protocol ID. Here's the path. So I know what the path is now. So I can make the actual request that I want to make. And I'm just using curl here. So there's no libp2p involved at this point. So there we go. So I've made the request to my protocol, and it has responded with hello from libp2p, which means that the request was handled by libp2p and not something else. So if I were to do a different URL, and I get a 404 back, which is falling through to the server. Great. We got there. That's cool. What about my favorite app server, my frameworks? Like, we're JavaScript developers. We love frameworks. Stick a framework on it. No problem. So we can totally do that. Let's have another demo. It's good, we're already set up for this one, so, you know, not quite so bad. So I've got a second one. So here we're gonna do the same thing, but instead of just using Node's built-in server, we're gonna use an Express app. So it's very similar. So I have my protocol, I have my port, I have my libp2p node, and then I have can handle, and then then I create an Express app, and then I just say hello from Express. And so in the server, I called it handle. If it handles it, great. If not, then I call Express. So instead of doing my own hand-rolled server, I'm just reusing someone else's existing application server, which is fantastic. So I can do node server, listening on the same port, and we can see the same thing. So if I do my protocol handler, I get hello from libp2p. If I do the arbitrary random URL, I get hello from Express. So this way we don't squat on anything. You can integrate it with your existing application, and you can just add libp2p superpowers to it. What about bidirectional protocols? So this is all very good and well if you're just doing simple response, request response protocols, but sometimes you might want to send a few more messages forward and backwards. Can we do that? Yeah, we can. So of course, if you want to do bidirectional things in web world, we use WebSockets, don't we? So here I have a simple web server. So again, we've got our libp2p node. We handle our protocol, except for we are now wrapping our route in a WebSocket route. And so that accepts a WebSocket argument, and it's a void return, so we can do anything we like in there. We can read data, we can send data. Create a WebSocket server. This one is from the WS library, because there's no built-in Node WebSocket server, unfortunately. So we have to go to userland. That's also why we need to pass the incoming socket to this toWebSocket function, which is exported from the libp2p HTTP server module. The reason being that the WebSocket server, like, we're trying to do everything as web standards as much as possible, and the WebSocket implementation from the WS module is not quite compatible. So this module just adds the methods that it needs, mostly around event emitters, to make it compatible with the web API, and we now have isomorphic JavaScript, and we're all happy again. So again, we have our HTTP server. We called it handle, and if we did handle it, great, and if we didn't, we hand it off to our app to handle. We process the upgrade, etc., etc. So I can run it in here. So actually, the client side, very simple. We just have a WebSocket, which is now global in Node. Hooray! So this does actually use the W3C API for it. So we're just going to print any message that we have, any incoming message that we receive. So I can do node server. my server is running, and then if I go into the WebSockets directory and I do node client, I hope everyone can see that, which is very small. I mean, it's big to me, but it's close to me, so, you know. And it says hello from libp2p, so this is now coming over WebSockets. All right, bi-directional protocols, who knew? Peer authentication. Okay, I'm going to talk about this a little bit, but I'm going to need to go back to the speaker notes because it's not 100% straightforward. Stop mirroring. Peer authentication. All right, so one of the nice things that we get from libp2p is we get the ability to assert that the remote peer is in possession of the private key that corresponds to its advertised public key. This in HTTP, and this works both ways. So that means that the remote peer also authenticates us. In HTTP, the client trusts the server. Trust is a dirty word in the distributed world. It trusts the server because it has an SSL certificate, and as we know, that means nothing at all. And the HTTP spec for libp2p adds some capabilities for verifying that the remote has the peer or has the private key that they claim to have. It has some caveats. So all your traffic has to go over HTTPS, otherwise you're vulnerable to eavesdropping, or you have to encrypt it somehow. So you might want to layer like noise or something on top of this. We do this in libp2p with WebSockets because you can't guarantee that you can't then just like send your data in plain text because you can't guarantee that the SSL certificate the underlying transport is using has not been compromised in some way. Big caveat. Big caveat. So how does it work? So we have two types of authentication. So you can either authenticate, you can either get the client to initiate the authentication, in which case the server will do the handshake. Well, the server will respond to the challenge before any data is sent, or we have it the other way around, where the server. Oh, actually, that's the other way around, isn't it? So this is the server initiated authentication. So we make the request, and then the server challenges the client to provide proof that it has the key, which is done through some signatures of through signing some information. Or we can have it the other way, where the client challenges the server first, and it does this before sending the request. So, for example, you may not want the server to know the resource that you're requesting, so you can send a challenge and get the server to authenticate itself before you actually make the request. Demos. More demos. Okay, back to a mirror. Back to a mirror. Okay, top tip for the mirroring. That's making life a lot easier. Okay, so we have server initiated authentication. So first of all, I'm going to go through. So it's very similar again. So we have the node that we've created, and we swapped out our WebSocket route for an authenticated route. So this now just means that we're going to get a peer ID as the second argument, and we're going to tell the requester what their peer ID is. The rest of it's all the same as before, so I don't need to go through that. Server, yes. So that's now listening on a web server, and then we can look at the client quickly. And what does the client do? So nothing really. So we've added peer ID auth middleware. So this allows the client to support authentication, and we don't do anything. We just make a request using the built-in fetch method and passing a URL. So if I pass a URL to this method, it just uses fetch behind the scenes. If I pass a multi-add, it'll actually go and dial over libp2p. So I'm just going to make the request, and I'm going to print out the response. So I have, in the server, I have my handler running on the protocol again. So I'll get into client, so I do node. Client, there's my URL, and then I want the protocol ID afterwards. So that's that. Ta-da! So it's made a request. This tiny little window down at the bottom. It's made a request, and we can see here are the headers that have come back. And then it's told me what my peer ID is, which is fab. So that means that so the server has demanded the client authenticate itself beforehand. We can see very quickly the client version. Like we just ask it to verify the remote peer. We have a function here so we can assert that the peer ID is the one that we expect. And we'll just print out the server's ID. So the interesting thing here is that on the server side, we can make the authentication optional. So if we pass in require auth false, then the peer ID becomes optional. It becomes undefined or possibly a peer ID. So if I can go into, I think I'll just do node, no wait, cd div 5, all right, node server, DJS, node, client, oh, hang on, wait, I need to use the, so there we go, and then the server has told us what our client ID is. No, I've done the wrong one. Should be server, yeah. No, wait, so yeah, so the client ID. So this is the server has told us what our own ID is. Hooray, it works. That was libp2p over HTTP, which is fine. That's all good and well. What if we turn the whole thing on its head? So instead of sending libp2p stuff over HTTP, we send libp2p stuff. Sorry, we send the other way. We send HTTP stuff over lib. Even I get confused. It's like, ah, dear. Maybe these things should be two separate modules, or at least two separate talks. That would be better, probably. Stop mirroring. Amazing. So in this version, we're going to use libp2p for routing, and then we're going to send HTTP stuff over it. More demos. That's the wrong one. Oh, God's sake. There we go. Okay, fine. So here we have a very simple server. So this goes the other way, right? So we have a libp2p node. Now you'll notice it's got more configuration. So we have a WebRTC direct transport. We listen on an address. And here we're passing a server to libp2p. So the server itself is a regular node server. And it just says, hello from HTTP server. So what I'm going to do is I'm going to go into the directory 6 and then start the server, node server. It's going to print an address out. So this is a WebRTC direct address. I have a little noddy peer-to-peer version of curl where I'm just going to make a request to this. I'm just going to make a request to this URL or this multi-header, sorry. Curl peer-to-p and then stick the multi-header in and I get a connection. So I've made a libp2p connection to this remote node and I've sent an HTTP request over it. And it's told me, hello from HTTP server. That's pretty cool because now I could have done that through, you know, I could have done it over Quick, I could have done it over WebRTC, I could have done it over Carrier Pigeon because we've used libp2p to actually do the routing layer and now we have an application layer within inside libp2p. That's pretty cool. Does it work on WebSockets? I don't know. I mean, yes, of course it works over WebSockets. I'm going to skip the next demo because it's very similar to that one. It just works over WebSockets. Okay. What about Indici? Like, what if you want to use like request, or you want to use, you know, the built-in fetch? Of course, yeah, of course you can use it. So let me skip this demo as well. But basically, you have in Node, you have this idea of HTTP agents, and you can use them to make a request. So you can get an agent from the HTTP service in Node and then make a request from it, and it will use that agent to then create the socket that it's going to send data over, and it will use libp2p to do the routing to get to the remote host, open the stream, the protocol stream, and then you can send data to a web service running on a remote libp2p node. That's super fun. And then obviously you can do the same thing in Indici as well, except for they call them dispatchers rather than agents, but it's all the same thing. So you can get a dispatcher, you hand it off to Indici, and then suddenly you can do this stuff over libp2p, which is amazing. That's all fine. That's all fine, good and well. If it seems familiar, some of the people who are slightly longer in the tooth in the room may remember this. Go libp2p HTTP. It basically used libp2p as the routing layer for HTTP, which if you hadn't noticed has been what I've been talking about for the last 10 minutes. So cool, it's alive and well. This particular module has been merged into Go libp2p. All of the examples so far have been JS libp2p, but it's all supported in Go libp2p as well. Hurrah. So where are we? We've gone from this kind of thing with HTTP, and now we're kind of here, because we can make requests to these servers. And all these little dots on the outside, I mean, they're kind of browsers. But what about the distributed web? What about the distributed web? Isn't that why we're all here? No, we're here for Ethereum. But like, sometimes we kind of got interested. Maybe we got interested into distributed stuff via the distributed web. So like, but what if the clients could be servers? Wouldn't that be cool? So then we move into this kind of model where like all the little dots around the outside are suddenly interconnected, and they can all do HTTP server things. I don't know if you've noticed, but in this diagram, which we see all the time, all the dots are actually in exactly the same place in each diagram, which makes it much easier to like create a graphic like this, because you just can copy and paste all the logos and just move them across. Brilliant. Old ways are best ways. Okay, demo. Final demo. Final demo. So here we have a distributed web demo. Right, so how am I going to do this? Okay, I'm going to come out of full screen. So, right. So what I'm going to do is I'm going to set up a relay and two web servers, two web pages. They need the relay, they're going to connect over WebRTC, so they need the relay to dial each other. Node. Relay. So now I have a relay running. Don't worry, you won't need to pay any attention to the terminal, because this is not in the terminal. So if I go to the server, npm start, I'm going to open that in a web browser. So I will make it bigger. Enhance. So I have a web page here. I'm just going to dial the relay. So connected to the relay, and now I have some WebRTC listening addresses. Great. So client node, no wait, npm start. Root. So now I have a web browser running in a web browser. I thought I'd make it look like, you know, so the way this is really working is there's an iframe in this window, and I'm going to load HTML from the server, which is running here, and I'm going to render it in the iframe, because obviously I can't use a web view. But there are limitations on what you can do. So like, also I can't, you know, maybe we could like try to inject JavaScript into the page, but like I don't know if it would affect the you know, the context of this injected within too. So I'm harking back to an era where JavaScript didn't exist. something a lot of people who are obsessed with WASM would prefer was now. JavaScript not existing, I mean. Anyway, so I've taken the listening address of this the server, and I've put it in the address bar, and I click go, and I've loaded the web page from a browser. Also, there's a great GIF under construction. Remember them? It turns out there's a website that's archived all the GIFs from GeoCities, and they're all available, which I spent a long time looking through. It made me feel great. Anyway, if you look back at the server, you can see the logs. So you can see that I've made a request to the root. It's been a 200, and then I've got a request to load the GIF. And like so, there's a link in here, so you can see the counter, hopefully. And I can increment this counter, and you can see it's reloading the page over and over again. If you check the address bar, you can actually see there's the HTTP the path is in there. And if I load the page again, so I'm just going to remove the path and then go again, and the counter will stay the same. I can reload the whole page, stick that address in. This proves that the state is not being held in the client, so the counter is still 6. So I could reload the server, and obviously now everything's reset, so I can do the thing, get another relay connection, and I go back to here, and I'll load it again, and the counter should reset to 0. Yeah, because it's being served from the browser, so I've restarted the node. Very quickly in demo land, so you can see in the server, I just have create server from HTTP server node. So this is running the browser. This is being bundled, but it doesn't have any node internals. So this create server function is actually it's the version from node core that's ported to just browser JavaScript, because it doesn't actually have any dependency on the internals of node. So you can run your own server in the browser. This way you can actually, so here's the page, security warning about not getting your stuff stolen. But yeah, you can see within the page that I've got exactly the same API as node, and we serve the page. That's it. That's the end. All the stuff is available at this URL. That's me. I'm making brain. This is the end, and I work for Shipyard. Please come and talk to me afterwards. I would love to talk about this stuff more. It's very exciting.
Thank you, Alex.